Hi everyone, and welcome to the October MAPP webinar. The topic of today's webinar is CMIP5 Evaluation. So we have 4 speakers who are going to focus on studies that have examined the Coupled Model Intercomparison Project Phase 5, 20th century results. We have 4 speakers, as I said, Justin Sheffield from Princeton University, Jianan Zhang from UCLA, Andy Barrett from the National Snow and Ice Data Center, and Zaitao Pan from St. Louis University. Justin's going to talk about a paper that was organized under the MAPP CMIP5 Task Force. It's a large group paper that's been co-authored by a number of MAPP-funded investigators on the topic of 20th century model simulations of CMIP5. So, Justin, are you on the line?
Yes, I am. Hi.
Okay, hi, Justin. So I'm going to switch control over to your computer. Great, looks good. So whenever you're ready, feel free to go.
All right, thanks, thanks Dan, and thanks for everyone for coming this afternoon. I'm going to talk about a synthesis piece of work looking at evaluation of CMIP5 models 20th century for North American climate. As Dan said, this is part of the NOAA MAPP CMIP5 Task Force. The idea behind the task force is to bring together funded PIs to attack broader questions, science questions that can't be done by a single PI alone. So you can see from the list of contributors, it's a huge long list. PIs there plus colleagues. So, you know, many contributions from many people. So the goal of this work was to, as I said, evaluate the 20th century historical simulations. And it's a synthesis of work across a range of climate features, right from the basic climate variables like seasonal temperature and precipitation to some more detailed, finer scale regional climate features, as well as looking at different timescales from intra-seasonal variability through to interannual, decadal, and longer-term trends as well. So a large scope to the analysis that was done. So, as I said, this work was carried out by multiple task force PIs, including new analysis by the individual PIs, and also leveraging from a Journal of Climate special collection, so individual papers by each of those PIs. So some of the analysis was taken from those, and our next 3 speakers are going to talk in more detail about particular analyses that were carried out. One note, number 4 here, on the actual climate models and ensembles that we use. Generally, turns out to be a different set for each of the different analyses, which depended on data availability. A lot of this data was only available at the beginning of this year, so there was a lot of downloading and processing effort, especially in the analyses that require high-frequency data, such as sub-daily. And so that has limited the amount of the number of climate models and ensembles that could be analyzed. Number 5, so models are evaluated for their ability to reproduce these observed climate features. We were also able to look at some CMIP3 data for some of the analyses. In other cases, we were able to look at previous studies, so looking in a more qualitative sense rather than a point-by-point comparison. So the presentation today, within 20 minutes, I can only show you a small sample of the breadth and the depth of the analyses that went into these papers. These papers are shown down below. Actually, it was so much that it got split into 2 parts. This has been submitted to Journal of Climate. The first part was on continental and regional climatology, and the second part on intra-seasonal to decadal variability. And then the third part is looking at the projections, which was led by Eric Maloney, and I believe there's going to be a future projection CMIP5 webinar next month on this topic. So the range of features that we looked at, I've grouped them here, 5 groups. The first one is continental climate, so that's the basic climate characteristics, precipitation, temperature, land, atmosphere, water budget, sea surface temperatures, and some other elements there for the continent as a whole. Number 2, We looked at some regional climate features. There was a whole list of different features there, from the North American monsoon through to Arctic sea ice to extremes in precipitation and temperature in various regions. Number 3, East Pacific and Atlantic tropical cyclones gets its own little group. And then a couple of groups based on the timescale of variability, so intra-seasonal. So we look specifically at intra-seasonal variability in the Eastern Pacific. Another example is midsummer drought in Central America, which I'll talk about a little here. And then the last group was looking at longer timescales, so interannual to decadal variability and some long-term trends. So that's obviously ENSO, AMO, PDO, plus teleconnections with North American climate as well. And things like the warming hole in the southeast that Zaitopan is going to talk about later, and trends in precipitation and temperature as well. This figure on the right is a poster from a CMIP5 workshop back in March, and just shows the kind of breadth of the analyses that were just starting to be done then, and then finally ended up in this paper that was submitted in July, or series of papers. Okay, so I'm going to go through maybe 15 slides that show some highlights of the work. Of course, I can't show everything here, so I'm just picking out a few of those, and starting with these basic climate variables. So the first one is seasonal air temperature. Basically, what we see on the left is wintertime climatology of surface temperature. On the right is the summer equivalent of that. These panels show, top left is the multi-model ensemble from CMIP5. Then the observations, in this case it's reanalysis, NSEP2 reanalysis, and then their difference is the third panel. And that's the same over for the summertime on the right. And then all the panels down below are individual models. And you can see for the wintertime and partly for the summertime, the patterns look pretty similar. All the temperatures from generally, well, for the multi-model ensemble are generally within 1 degree of the observations. Of course, these observations have some uncertainty in themselves, and this is true for most of the observations, well, for all the observations that are used in the different analysis. There's some uncertainties there which kept in mind. So overall, the patterns look quite similar within 1 degree of observations. If you look at the summertime, you see some differences, but the models generally do well, especially as an ensemble, of getting this extension of warmer temperatures in the summertime over 30 degrees. Get there in the ensemble. And then it's also this extension into the Canadian prairies of temperatures greater than 10 degrees. In the wintertime, the 0 degree contour is fairly well picked up by the multi-model ensemble versus the observations. So generally okay for seasonal air temperature. This is an equivalent slide for seasonal precipitation, shown in a slightly different way. On the left here is the wintertime and summertime climatology of precipitation from the CMAP observations, and below that is the CMIP5 ensemble mean. Again, for the 2 seasons. Over on the right, I'll talk about this in the middle, is some contours for individual models, so you can see the spread. So back to the climatology and the multi-model ensemble on the left, again, you can see that the CMIP5 ensemble picks up the broad features of precipitation on seasonal timescales over North America and the adjoining seas. There tends to be a large spread in individual model performance regionally. For example, there is too much precipitation in the continental interior, especially in the summertime, and too much spatial spread in the wintertime storm tracks as well in the models. And if you look at individual models over here on the right panels, again we have this column here is for wintertime, and then summertime on the right. Are actually in the blue shading. This is for the 3 millimeter per day contour. So it's like an index of major precipitation features. So the observations are the blue shading, and each of the lines is an individual model. And you can see there's some real outlier models there that cause some of the biases that you see. So another thing we looked at was the water budgets for the atmosphere and the land. This is crucial for understanding the precipitation and how that gets filtered down into some of the variables that impact our lives on the surface, so runoff and evapotranspiration and soil moisture and snow. So starting on the right here, this is the atmospheric side of that budget in terms of vertically integrated moisture transport. So that's the vectors on each of these maps. It's divergence or convergence, which is the contours in the shading. And again, we have the season split, so summertime now on the left and wintertime on the right. And then the top row is the observational estimates from the 20th century reanalysis. And then we have 4 model estimates. So again, this is constrained by the available data or our ability to process the data, because this needs high-frequency data, 3-hourly, 6-hourly data to actually do this. So we only have 4 models to look at. But overall, they get the convergence happening over the eastern side of the U.S., some divergence in the middle of the country, and then convergence over the west in general. But they fail to pick up these stronger convergent features that you see, especially in the summertime over the Rockies and the Mexican Plateau. But overall, not bad. And some of these features may, of course, be correlated with a lack of fine resolution in some of the models, in most of the models. Over on the left, over here, just some examples of the land part of the water budget. And the example shown here in these small panels is precipitation seasonal cycle for evapotranspiration runoff, change in storage at the surface, so that's soil moisture and any surface water that's in the models, and then snow water equivalent, so essentially the snowpack here. And then the black line is the observational estimate, and then the final lines, the gray lines, are for individual models. 12 models are shown here. And you can see for this particular region, which is western North America, I think, for this example, so approximately this region here, precipitation is overestimated. This leads to an overestimation in evapotranspiration, but we actually have seasonal differences in the bias in runoff that may in part be related to biases in the snow water equivalent. The actual change in storage over the season looks reasonable. So overall, the models have a reasonable seasonal cycle of terrestrial hydrology, but there's generally biases in each region in precipitation. This filters down into biases in things like evapotranspiration, runoff, and snow accumulation. So overall, not bad. This map here just shows the mean annual runoff from a land surface model estimate over here, and then the model. So the spatial pattern is pretty much okay. There's some regional differences, and then there tends to be a general overestimation over the whole continent. Next slide is another example of continent-wide climate. This is in terms of biophysical indicators related to temperature. So the examples I'm showing here are growing season length. This is basically the time between the last frost in the spring and then the first frost in the fall. The number of summer days over 25 degrees centigrade, I think it is. And then the number of frost days is on the bottom row. And we have observations, the CMIP5 ensemble, and then their difference over on the right. If you look at the first 2 rows, you can see that the patterns, the spatial patterns, look pretty good. Looking at the differences, you can see some regional problems with the models. So overall, the model's growing season is generally too long. Large positive biases up to 40 to 50 days in the central U.S. And then you have some more regional features, coastlines, bigger biases, and around the Great Lakes. That may be more to do with what features the models can actually pick out, given that they are pretty coarse in their resolution. For number of summer days, the frequency in the models is too low in western regions, and then the frequency of frost days is too high in western regions coming up into Alaska here for most models. But overall, the spatial patterns look pretty good. Another interesting aspect is the frequency of persistent wet and dry anomalies. So dry anomalies is essentially drought. And so we're looking at this in 2 ways. On the left here is in terms of precipitation anomalies. On the right is in terms of soil moisture anomalies. And if you think about this on the dry side of things in terms of drought, then here we're representing the frequency of meteorological drought And then on the right, this is the frequency of agricultural drought. But we're also looking at the other end of the spectrum in terms of persistent weather anomalies as well. So the observations for precipitation show this gradient between lower frequencies and higher frequencies in these persistent events. And the models have a mixed range of skill in representing this gradient. Some models get it, other models get the opposite gradient in terms of the geographic distribution. And it turns out that the ones that tend to get this gradient okay also have a realistic precipitation climatology. So that's a good thing to know. The problem is if you look at the soil moisture anomalies, these persistent anomalies, there really is a mixed bag of skill going on here. Again, we should be seeing this kind of gradient between low frequency and higher frequency in the west. Some models get it, a lot of models get it completely wrong. And there is no direct correlation between good performance in precipitation and good performance in soil moisture anomalies. So this indicates that even if you get the precipitation right, you need a pretty good land surface hydrology model in the climate model to actually translate those precipitation anomalies into realistic soil moisture anomalies. So now switching to some more regional features. Just going to give a few examples here. This first one is on western North Atlantic winter cyclones, so very important for delivery of precipitation to the northeast of the continent. So this panel on the left, series of panels, shows the frequency of cool season cyclones. This is from CFSR, so this is a reanalysis estimate, and this is the CMIP5 multi-model mean. And you can see that the spatial pattern looks pretty good. There's a slight underestimation overall, about 10 to 20% in that frequency of cool season cyclones. And then there's some example individual model results, and you can see that turns out that the models that tend to bring it down are the coarser resolution models. So again, with higher resolution, you become a little bit more realistic in representing the observational data. This other panel on the right is the distribution of cyclone intensity. So the fine lines are individual models. The red line is the CMIP5 ensemble mean, and then the observational estimate from CFSR is the blue. And you can see it does a pretty good job. CMIP5 does a pretty good job. There is a bit of underestimation of the frequency of these stronger cyclones over here, as indicated by this is sea level pressure here. So overall, pretty good. I'm not going to say too much about these slides here, but just to highlight a couple of panels. We're looking at seasonal precipitation for the northeast in the wintertime, and also southern tier states for all seasons. And then these distribution panels here and here basically show the distribution of the frequency distribution of daily precipitation events. And the take-home message is that most of the models underestimate the heavier precipitation events. You can see that for the cool season in the northeast over here, and also for the southern tier states in all seasons, but especially in the summertime. And I haven't shown it here, but this is another feature that you see for temperature as well, for the hottest temperature maximums as well. There's an underestimation of those extremes. Another regional feature is the North American monsoon, which is very important for northwest Mexico and the southwest U.S., bringing about up to 70% of total annual rainfall during the monsoon season in approximately May through to the middle of or the end of summer. So these figures here, we actually have two sets. One is the CMIP5 data, which is the top row, and we also have some results from a previous study looking at the same metrics for CMIP3. And Yolanda Serra from the University of Arizona did this work, and they've her and her colleagues have split this into the models into three types. Firstly, those with a small phase error, so they actually get the timing of the peak of the monsoon okay. Models with a moderate phase error, so that's a 1 month lag from the observations. And then a handful of models that are actually biased by more than once in terms of their phase error, so they get it pretty wrong. And you can see that the CMIP5 generally shows a better onset compared to CMIP3. There's a lot of spread going on here. But it has difficulty in ending the monsoon. It should be dropping down in September, October, but a lot of these models carry on precipitating through the winter. and this is something that we saw in CMIP3 as well. And also a lot of these, there's a few models that have considerably higher positive biases in the overall maximum monsoon precipitation that we didn't see so much in CMIP3. So something's better, something's worse with particular models. Another thing that we looked at was tropical disturbances and cyclones. So this was done in two different ways of tracking disturbances and cyclones. The one on the left actually tracks all combinations of storms, disturbances, and cyclones. And the comparison here is in terms of storm track density against the ERA interim. And this is a 7 CMIP5 model mean. And you can see that the distribution looks pretty good in the East Pacific and also in the Atlantic, the tropical Atlantic as well. And then these other panels are results from the individual models that go into this mean result in terms of the differences. And you can see there's a lot of spread amongst the models. So although the mean looks pretty good, individual models give you quite a broad range in their simulations. Over on the right, this is similar kind of analysis, but focusing on tropical cyclone-like storms, so the more powerful storms, tropical storms, and hurricanes. And this is showing storm tracks from the models, and the observations are down here for the last 50 years. And you can see all of the models severely underestimate the frequency of tropical cyclone-like storms. Some models, like this HADGEM2, do a very poor job. Others are getting a bit closer. And this is, has important consequences for the production of precipitation over places like the southeast, which can actually get 20% of annual and 30% of warm season precipitation from tropical cyclones. And it contributes significantly to heavy precipitation as well. So we, colleagues at GFDL, Ming Zhao, provided some results from high-resolution modeling of tropical cyclones, and it's fairly well known that you need to have higher resolution models to actually pick up these tropical cyclone-type storms. So this is just some example results showing observational data here, similar to before, and then the C180 high-RAM model from GFDL showing a pretty good correspondence with the observations in terms of location, landfalling storms, and the actual frequency of those. And that is summarized over on the right in terms of the seasonal cycle of the frequency, so the number of storms over the seasonal cycle for the North Atlantic and the East Pacific, and you can see that they match up pretty well. One caveat is the model still cannot simulate the most intense storms, but you can see the improvement when you go from the climate model, the general climate model resolution, to this higher resolution of 25 to 50 kilometer resolution. Another feature, now we're turning
Justin, this is a 20-minute warning.
Oh, okay. Let me skip a couple then, and I'll just focus on a few. Maybe look at the ENSO here, and then I'll try and finish up.
Okay, thanks.
So we looked at ENSO, very important for a number of teleconnections, and I just want to focus really on these bottom panels, which are evaluating the teleconnections between the CMIP5 models and their predicted North American temperature and precipitation. The observational patterns are here, and we can see the well-known gradient in the impact on temperature for La Nina and El Nino, and precipitation, especially in the southern tier states. And these are the results for the models, and they basically do very poorly in picking up these teleconnections. And this hasn't changed much since CMIP3. This is another facet of ENSO, the Central Pacific ENSO and the Eastern Pacific ENSO, and the teleconnections with winter surface air temperature. And essentially it changes depending on which type of ENSO you have. And then if you look at like how things have changed from CMIP3 to CMIP5, in terms of predictions of these two different types, there used to be a strong group and a weak group in CMIP3. Now the models have tended to group together, and the weaker ones have become more similar to the stronger ones, so a single group. And then in terms of the teleconnection, turns out there's probably about 5 CMIP5 models that can simulate these two types of ENSO, as well as their different impacts on U.S. winter temperatures. And of course that means there's a whole bunch of models that can't do that. We also looked at PDO. The ones to look at here are essentially these two panels, observational pattern of SSTs for PDO. CMIP5 does a pretty good job, and that is carried on from CMIP3. and then the teleconnections over here. Observations in the top for temperature and precipitation, and the models do a pretty good job of picking that up. The only place where they fail is over the eastern US for the precipitation teleconnection, but overall pretty good. I'll skip this in the interest of time. This was just trends in precipitation, and skip this as well. And I'll just give you a couple of conclusion slides that looked at CMIP3 versus CMIP5 and the question of have the models improved. Overall, I think they haven't improved dramatically. Some variables like SSTs and surface air temperature were already well produced by CMIP3, so any improvements are pretty difficult. PDO variability remains reasonable in CMIP5. AMO, which I didn't show, also appears to improve slightly with CMIP5. For ENSO, they can reproduce the frequency and mean amplitude okay, but the teleconnections are still poorly reproduced. And then a couple of last points here. Some models have improved for certain features. There are actually other models that have become worse, and there's some examples there. And then finally, conclusions. Overall, the models do pretty well in capturing the broad-scale climate features of North America. Resolution can explain many of the biases, and there's a list of regional features where resolution of the models comes into play. But then again, testing these regional climate features is a pretty difficult test for these coarse resolution models, and some of them actually do fairly well. As I said, CMIP5 relative to CMIP3, not a huge improvement. We've only analyzed a handful of models so far. And there are several outstanding issues, such as underestimation of extreme temperatures and heavy rainfall, and some other features I've listed there. And of course, these results have implications for how we view the future projections, and that's going to be next month's webinar. Okay, so thanks for your attention, and I'll stop there.
Thanks so much, Justin, especially for summarizing so much excellent work in such a short period of time. Justin, are you going to be around at the end of the webinar today for questions? I can't remember if you had to leave early or not.
I have to leave early, so I apologize for that. I have to pick up the kids.
Okay. Yep, that's a good excuse. Justin, would you be willing to take a question or two right now since you won't be, be around? So are there any questions in the room here? Okay, I have to unmute folks on the phone in order to hear if there are any questions online. Okay, so are there any questions on the phone line? Okay, if there aren't any questions on the phone line, Jinan, are you there?
Yes, I'm here.
Okay, great. I am making you a panelist, and hold on one sec while I transfer that to your computer. One more thing to mention about Justin's talk, which is that if anyone would like additional information about these two papers, they are posted on the MAPP website currently, and they'll be up there. You can download them in PDF form. They'll be up there until they're accepted, and then won't be available online again until they're published, or in pre-publication version. So feel free to go to the CPO MAPP website if you'd like to take a look at the two papers that Justin discussed. Okay, Jinan, did you email me a copy of your slides?
Yeah, maybe I still had the older version. I did not send it successfully.
Okay.
So can you just display? Maybe I will skip some slides.
Sure, I'm just downloading them right now, and bear with me for a moment.
While Dan is doing that, I just wanted to add that the MAPP website also has many of the individual papers that were written by the CMIP5 Task Force members, so you can download not only the overview papers, but also individual papers which really have more depth on each topic. Just wanted to add that.
Yeah, thanks. Okay, so Jinan, can you see the slides on your screen?
Yeah, I can see.
Okay, so just tell me when to advance the slides, and you can start whenever you'd like.
Yeah, okay. So, yeah, good morning or good afternoon, everyone. So, firstly, I want to acknowledge my collaborators for this study, including Alec Maloney from CSU and Frank Lee, Dan Wallace at JPL Caltech. Next, please, Dan. So as we know, the intra-seasonal variability of the Eastern Pacific exerts significant influence on regional climate or weather systems. including the tropical cyclone activity, the North American monsoon, also the Caribbean Sea, the precipitation low-level jet, as well as the gap winds over the Central America, possibly the El Nino. So I will not emphasize more on this. Next, please, Dan. So this is the following 2 slides. I will try to very briefly introduce you the characteristics of the intra-seasonal variability of the Eastern Pacific based on observations. So on this slide, the right panel, the plot shows the time evolution at every 3 days interval, the anomalous rainfall, which is shaded. Red means the enhanced rainfall, blue means reduced rainfall, and also the surface wind anomalies with vectors. So we can see during the ISV, the Eastern Pacific ISV evolution, the convection first appears over the western side of the domain, then slowly propagates eastwards and intensifies. Then during this period, the northward propagation can also evident. The one important feature associated with this ISV over the Eastern Pacific is for example, the day 18, you can see the enhanced convection over the Eastern Pacific is associated with the southwesterly anomalous winds. And considering over this one pole, the Eastern Pacific one pole region, where the ISV is most active, you can see the left lower panel, over this region is characterized, the summer mean surface wind over this region is characterized by the westerly wind, or generally very weak winds. So in this case, the southwesterly anomalies associated with enhanced convection will lead to enhancement of the total wind, then lead to the increasement of the latent heat flux, which will further feed the moist energy to the already the active convection. So this provides like the positive feedback. This positive feedback is found to play a critical role for the growth of the ISV convection over the Eastern Pacific, based on the previous study by Maloney and Asperson in 2003. However, I should note that this positive feedback is only valid in presence of the westerly summer mean flow or very weak mean flow case. So next slide, please, Dan. So next slides will provide a brief the hormonal diagram. The upper panel shows the time on the y-axis. The x is the longitude. So this is shows anomalous rainfall evolution. So if we focus on the right-hand side, it's over the Eastern Pacific. We can see this eastward propagation associated with ISV over the Eastern Pacific. Then also if we extend to the Indian Ocean and Western Pacific sector, we can see the ISV over the Eastern Pacific tends to be closely associated with the eastward propagating signal from the western side. And the lower panel shows the y direction is the latitudes, and x versus time. You can see clearly the northward propagation associated with the ISV over the Eastern Pacific, which is very similar to the northward propagation of the monsoon intra-seasonal variability over the Indian Ocean. So next slide, please. So based on considering the critical role of the intra-seasonal variability over the Eastern Pacific, and as essential tools for climate prediction and projection, it is necessary for current GCMs to realistically capture this important form of variability, particularly when we project the future activity of the extreme events, which is the strongly modulated by this intra-seasonal variability. So in this study, we evaluate how the intra-seasonal variability over the Eastern Pacific is simulated in the latest CMIP5 models. This is a part of the collaborating efforts led by the MAPP program. Next, please. So we analyzed the 25-year integrations based on the 16 CMIP5 models. Next, please. So firstly, we evaluate the summer mean rainfall pattern, which is shaded here, and 850 winds, which is vector. The left upper panel is observation, and the others are the model simulations. So we can see that over the Eastern Pacific, the observed rainfall pattern is mainly characterized by elongated ITCZ belt, as well as the North American monsoon. And this feature is generally reasonably captured by most of these models, although the model bias is also noted. For example, some model try to emphasize maximum rainfall over the western side of this domain. And also, most of these models try to overestimate the rainfall near the coastal region over the South America. So in the wind pattern, in the observations, upper left panel, you can see mainly it's the convergent flow onto the Eastern Pacific ITCZ. Over the Eastern Pacific warm pole region, which is labeled by the blue box, generally consistent with previously slides, it's generally characterized by the westerly summer mean flow or very weak flow. And this pattern is relatively well captured by several models. For example, the middle upper panel, the two Hadley models, but the several other models shows the large bias, and they capture the very strong easterly mean flow rather than the weak westerly as in the observations. So this will be further more clear in next slides, which is the average zonal mean wind, U component wind over the Eastern Pacific warm pole region. So the y-axis is the average, domain average, the U wind. We can see the positive means westerly and negative the easterly. So the x direction is the observation, and as well as simulation in the different models. Again, in the observation, we can see a weekly westerly the summer mean low-level winds. The next slide, please. Next, please. So, and you can see that in the three models, that shows realistic, very weak westerly summer mean flow. Also, the other three models shows relatively weak the easterly mean flow, low-level flow. While all other models that shows a very strong, the large bias in capturing the summer mean flow over the eastern warm pole region, which shows very large easterly winds instead of the westerly in the observations. So next, please. So here, then we apply the complex UF approach, try to extract the leading ISV modes over the Eastern Pacific. This approach is mainly follow Maloney et al. 2008. So the one advantage of the complex UF is because the eigenvector is complex, it can capture the propagation features by just the leading EF modes rather than the one pair based on the traditional UF or extended UF. So if we apply this combined UF analysis to the 30 to 90-day bandpass filtered trim rainfall during body summer over the Eastern Pacific domain, shown in the lower panel, so we can derive the spatial amplitudes and the spatial phase distribution of the leading ISV modes over the Eastern Pacific. So for example, the maximum amplitude is confined over the Eastern Pacific warm pole region. And also based on the spatial phase of the leading modes, we can see the propagation direction, which is indicated by the gradient of the spatial phase. Next, please. So, for example, for the leading ISV mode over based on the observations, as we previously mentioned, it's mainly there is the eastward and the northward propagation component. Next, please. So then we apply this combined UF approach to all the all other the model simulations. We can see this slide shows the spatial amplitude distribution for the first CMIP5 mode. So the left upper panel is again is observation, and others are the model simulation. We can see the spatial amplitude pattern is reasonably well captured by several models. For example, the French CNRM model, and also the Hadley models. Although some models try to overestimate the amplitude, while other several models, the amplitude is very weak in other models. For example, panel J, it's the Russian model. Also, the last one is the panel Q. Next, please. So this slide shows the spatial distribution of the phase of the leading UF1 mode based on observation and models. So we can see the upper left panel observed that the northeastward propagation tendency associated with this leading ISV mode is reasonably well captured in several models. For example, the panel D, the French model, and the panel E, also the GHI, the Hadley Center model. And however, in other several models, for example, the panel J, K, and I, and these models shows different opposite the propagation feature, so which is unrealistic. So next, please. Then, based on the previous, we showed that the spatial amplitude, the distributions, if we times this with the cosine or sine of the spatial phase distribution, we can get the physical distribution of the leading UF mode based on the model and observations. Then we can calculate the pattern correlation between the model against the observations, and we sort the pattern correlation score on the x direction in these slides, and the y direction shows the relative amplitude of the leading mode against the observations. The amplitude, the above 1 means the stronger than observed. The less than 1 means the weaker than observations. So we can see that generally on the right-hand side, the several models shows relatively higher pattern correlation. With the pattern correlation, the score greater than 0.75. Although the amplitude, there is also bias in the amplitude of these models. Some model overestimate and some model underestimate of the observed amplitude. Then next, please. Then if we further label some models which shows the westerly more realistic the summer mean flow by showing the westerly or weak easterly mean flow at 850 millibar as in the observations as square, and for those models display the unrealistic summer mean flow by showing very strong easterly flow with the circle, and the 2 diamond the marks represents the missing data in these 2 models. So generally, it's very interesting. We can see those models which shows the relatively higher pattern correlation, shows more realistic, captures more realistic summer mean flow over the Eastern Pacific, while those models shows the relatively less the predictive score for the intra-seasonal variability shows the unrealistic summer mean flow. So this notion can be further elaborated by the next slides. Next, please. So this slide shows the anomalous the surface latent Kita flux pattern, which is shaded, and red means the enhanced surface Kita flux, and the blue is reduced, and also along with the anomalous winds at 850 millibar, and this based on the observation and the different models, and this is the pattern is derived based on the regulation pattern at day 0 against the rainfall over the eastern the Eastern Pacific domain as labeled by the green square in the upper left panel. So we can see based on the observations, again, associated with the enhanced convection, that is southwesterly anomalous and enhanced the latent heat flux. And this configuration of the anomalous latent heat flux and anomalous wind is generally reasonably well captured in several models. And for example, the panel C, panel F, panel J, and this model generally captures a more realistic the summer mean flow, low-level flow over the Eastern Pacific. While over other models, for example, over G, shows not very organized latent heat flux pattern, the shading pattern. Even the sun is opposite. So actually, we also noticed that the wind anomalous in panel G, for example, actually shows reasonably well the westerly and the cyclonic circulation, but due to the large bias in the summer mean flow, which is the strong easterly in this case, so the latent heat flux is opposite sun. So in this case, the positive feedback, as we previously mentioned, for the intra-seasonal variability is missing in these models, which leads to the relatively the weaker score, the quality in simulating the intra-seasonal variability. So next, please.
Hi, Jianan. We've gone over 15 minutes, just so you know.
Yeah, okay. So I will go very fastly, and maybe I will skip this one.
Okay.
The next, please, yeah. So next one shows the Haumuro diagram. The y direction is the time, x direction is the longitude. So generally show the eastward propagation associated with the leading mode of the intra-seasonal mode based on the observations on the left upper panel and the model simulations. We can see that again in the observations, it's very clear the eastward propagation associated with the ISV over the Eastern Pacific. And this is relatively well captured by several models, for example, panel D, panel E, and the 3, the GHI, the Hadley Center models. But however, as we previously mentioned, the close linkage between the ISV over the Eastern Pacific and the Western Pacific, as found in the observations, is only captured by one model. It's panel D. And other models, although, for example, the Hadley models, although they capture the intra-seasonal variability, the pattern over the Eastern Pacific is reasonably well. The linkage between the two basins, between the Eastern Pacific and the Western Pacific, is not very clearly seen in these models. So these results suggest that, based on the model, at least based on the model simulations, the intra-seasonal variability over the Eastern Pacific could be sustained by itself. So, yeah, next slide, please. So I will go to try to summarize my main results. So among the 16 CMIP5 models we examined here, only 7 GCMs capture the spatial pattern of the leading ISV modes, and even these 7 models shows bias in capturing the amplitude of this intra-seasonal variability. And we found that the model fidelity in representing the Eastern Pacific ISV is closely associated with the model ability in capturing the summer mean flow. And the last one is based on the multi-model simulations. The results suggest that ISV could be sustained over the Eastern North Pacific without the forcing from the MGO over the Indian Ocean and the Western Pacific. So that's all. Thank you very much.
Thanks a lot, Jianan. Our next speaker is Andrew Barrett from the National Snow and Ice Data Center. Andy, are you on the phone?
I am.
Great. I'm going to try switching control of the webinar over to your computer. Okay, great. Yeah, we can see your slides, so just go full screen, and whenever you're ready, go ahead.
Okay, all right. Hello, everyone. I'm Andy Barrett from the National Snow and Ice Data Center, and I've been working with Julian Strove and Mark Serez, who's not mentioned on here, evaluating the representation of Arctic sea ice in CMIP5 now, but we look a little bit backwards at how they did in CMIP3 and try to see if we have any improvement in the representation of sea ice. So this figure is from a paper published by Julian in 2007, and the title of the paper was that faster than forecast, and the point was that the models, the trend in sea ice decline in the models is quite a bit slower than what we observed. This figure is showing the model ensemble from CMIP3 used in the IPCC-AR4. The black line, the thick black line, is the multi-model ensemble mean, and then the dashed lines are the plus and minus 1 sigma standard deviation. The red line is the observations, and this is a combined data set combining the Hadley sea ice data set with the NSIDC sea ice index. And we've added the record low September sea ice extent for 2012, which was 3.61 million square kilometers, the lowest we've seen in the observed record. And this just reemphasizes the point that the models were not matching the rate of decline that we have observed. So we wanted to see how we were doing in CMIP5. So we look in this analysis pretty much exclusively at the RCP 4.5 projections. We include that so that we can go from 1953 through to 2011. The CMIP5 historical runs end in 2005, so we just splice on 6 years of data there, which gives us 77 ensembles to choose from for the extended historical period. And we use a number of metrics. First of all, we look at how the models represent the 1953 to 1995 climatology in sea ice extent. We also look at how the models represent the seasonal cycle, and then look at how the September and March ice extent evolve through time and the trends. We also look at volume and thickness, and these aren't variables that are well measured in the Arctic. We either don't have particularly long time series, or we have to rely on reanalysis estimates of volume in particular. So these are the metrics that we've chosen to look at, and I'm going to run you through some slides and show you how the CMIP5 models are doing. So first of all, we're looking at climatology, and we choose the 1953 to 1995 period, largely because that takes us up to the point before sea ice extent tends to make a faster rate of decline. These two figures show September and March ice extent for a suite of models. We've chosen to represent the models as the distribution of ice extents represented by box and whisker plots. These are little space invaders that you see on the figure here. They're pretty standard box and whisker plots. The box in the middle shows the interquartile range. The black line shows the median of the distribution. The whiskers show the 10th and the 90th percentile range, and then there's a diamond in the center there which just shows the mean. The red line, the red horizontal line, is the observed mean sea ice extent for the 53 to 95 period, and the green line is the observed minimum and maximum sea ice extent for these 2 months. The width of the boxes represents the number of ensembles that are included in the distribution. So wider box and whiskers means more model ensembles, and several models just have a single ensemble that we can use. So let's focus on September to begin with. I think the one standout item here is this large positive bias for this particular model, and that's the CSIRO model that you'll see that this stands above in extent and volume throughout all of the analyses. There are some models which certainly are biased low, but they still tend to crop into the observed maximum and minimum range. So we can't dismiss them completely as being bad models, because they to some extent manage to capture the observed sea ice extent. If we look in March, the picture's a little different. There seems to be no consistency between how well models do in March and how well they do in September. But in general, there tends to be an overestimate in extent, but there are several single ensemble members which certainly fall a lot lower than we observe. But a lot of models, especially in September, are tending to fall within the range of observed minimum and maxima. So we're doing reasonably well there. If we switch to looking at how the models represent the seasonal cycle, here the box and whiskers represent the ensemble of the seasonal cycles for CMIP5, which is represented in the light gray box and whiskers, and CMIP5, the darker gray box and whiskers. The box and whiskers represent exactly the same as the previous slide. See that, and the red and green lines represent the observed mean and max and min. So the seasonal cycles are pretty well represented. CMIP3 tended to overestimate some of the long-term monthly means, especially in winter. And CMIP5 tends to do a little better, certainly falling pretty much within the observed range for the in spring and in September in particular. So we're on track to being able to match September sea ice extent quite well when we look in terms of the ensemble mean. The range of CMIP3 between the winter maxima and summer minima extent is somewhat smaller than what we're seeing in CMIP5, and again, CMIP5 tends to capture that range as in terms of the observed a little bit better. So if we switch to looking at the evolution of September extent, this is essentially the same figure as I showed at the start of the presentation, where the colored lines represent all the models that we include in the CMIP5 ensemble. The dotted dots represent the individual model ensemble members, the solid lines the model ensemble means. The black line is the multi-model ensemble mean, so taking all the models and calculating the mean for each month. And then the red line is the observed September extent. And again, the CSIRO model stands out as being much too high, and certainly not following the observed trajectory at all. But when we look at the other models, there's a wide spread that the ensemble mean pretty much traces the observations up until about 2000, when the observations or the model diverges from the observations. But I think if you look a little bit further along in time on the ensemble mean, then you do see some more dramatic drops in sea ice extent that are similar in character to the observations. So I think we're getting in the right ballpark, but the timing of the decline in sea ice extent is maybe a little off. Although I think there's no reason to expect that we will match the timing in terms of the historical observed record, because the interannual variability of the models is not necessarily the same as the interannual variability of the climate that we have. So by and large, we're doing quite well in terms of matching the evolution of ice extent. Here, this inset diagram allows us to look back at how CMIP5 was doing, and we can see an improvement, I think, over what the CMIP5 sea ice extents were doing. As I say, we're on track for 1953 through to about 2000, and then we start diverging. We were quite a bit off with CMIP5. So that's good news there. If we look at March, the differences aren't as stark. I don't think that should come as much of a surprise. The March extent is somewhat pretty well constrained by the Arctic basin. So if you fill up the Arctic Ocean with ice, there's not much else ice that you can generate. So we're doing quite well, though, in terms of March extent. If we turn to look at trends, here I'm showing CMIP5 trends, and now we're switching to looking to the 1979 to 2011 period. We do that because we think it's okay to look at the longer period before satellite records for looking at the long-term mean, but when we come to looking at trends, we feel we need to concentrate on a more reliable satellite record. So we focus on 1979 to 2011. And this figure really reinforces the message of Julien's 2007 paper, which is that we were seeing a decline in the observed decline that was faster than was represented in the models. Just to explain the figure a little bit, the dark and light gray shading shows the plus and minus 1 and 2 sigma confidence intervals for the observed trend. And here, when we calculate the observed trend and the confidence intervals, we take into account the autocorrelation between individual years. The colored symbols, the dots or the symbols themselves represent the mean trend, and the bars represent the plus and minus 2 sigma confidence intervals. So where we see a bar overlapping with the observed confidence intervals, there's no significant difference between the observation and model trend. And when we see those bars overlapping with the zero trend line, then the trend is not significantly different from zero. So most of the signs, most of the symbols are well above the observed trend. When we look at the multi-ensemble mean here at the end, we see that it's not significantly different from the observations, but it's also not significantly different from the zero trend line. So there, CMIP5 didn't really capture the trends and the observed trend, and there was really no dramatic trend to speak of in a statistical sense. If we shift to looking at CMIP5, I think we see a slightly better picture. It's not dramatically different. We're certainly seeing more ensembles shifting down towards the observed trend. We're still seeing some outliers, but when we look at it in terms of the multi-model mean here at the end, the mean trend has certainly shifted down towards the observed. There's a significant overlap between the observations and the multi-model mean, but again, the confidence intervals bars are pretty wide and still encapsulate the zero trend line. So are we seeing a trend in the models? Well, statistically, no, we're not. So a little disappointing there in model performance. So I'm going to switch up a little bit and move from looking at extent to ice thickness.
Hi, Andy. This is about the 15-minute mark, just to let you know.
Okay, thank you. So I'm going to move through this pretty quickly. If we look at the March extent here, I've got a subset of models, and we're comparing this with the spatial distribution of thicknesses from ICEStat for 3 years, February, March, April, and February, March, 06, 07, 08. The take-home here is that none of the models we show here really capture the spatial distribution of sea ice thickness. There tends to be thicker ice in the observations up against the Greenland and coast and the Canadian Arctic archipelago. We tend not to see that at all in any of the models. Maybe a little bit in CNRM at the top, middle of the top row, and maybe a little bit in MPI, but we don't see this Greenland to Siberia gradient across the Arctic. So we're not really capturing that spatial distribution particularly well. We are, however, doing reasonably okay for some models in matching ice volume, which is the product of extent and thickness, but there are some significant outliers. We've called out a couple here, the GIS model and the CAN ESM2 model outliers here, and we're making this comparison with the PMS simulated ice volume. I'll skip over, well, briefly just mention that the ice thickness in September, again, we're not capturing that spatial distribution of ice thickness that we see from ICESat. And we're certainly not capturing the summer minimum ice volume when we compare it with the PMS ice volume. So, in summary, the CMIP5 models to some extent better capture the observed decline in Arctic sea ice than CMIP3, but there are certainly some models that really stand out as not doing so well, others doing reasonably well. The models tend to exhibit a stronger seasonal cycle, both in extent and volume than CMIP3, and in observed, although I think they match the observed a little better. And there's still considerable intermodal scatter in terms of ice extent, volume, and thickness. And we're really not getting the spatial variability of thickness, which probably has a lot to do with the dynamics as well as the thermodynamics of ice in the Arctic. Thank you very much.
Okay, thanks a lot, Andy. Our next speaker is Zaitao Pan from St. Louis University. Zaitao, are you on the line?
Yes, I am.
Okay. I'm going to switch control over to your computer. Okay, great. So whenever you're ready, go ahead.
Okay, and this work and just analyze model skills in capturing so-called warming hole. Actually, it's an anonymous cooling area, and this work has been done by myself and in collaboration with Sanjay Kumar and Jim Kinder at COLA, and also my colleagues in China, or Chinese Academy of Sciences. And first, I will just briefly introduce what's the warming hole about. And second, I will examine the model performance in capturing this abnormal cooling, and based on 25 models and over 100 ensemble members. And next, I just very simply to try to figure out what is causing this warming hole. And lastly, I will use a method called like record-breaking frequencies as a metric for climate change. This is based on smaller subset of models. And here, I call it global warming holes. Actually, it's a cooling area. And warming hole, that means warming less or even cooling. that's why I give the name is a warming holes. Actually, here you see 3 warming holes, and U.S. one, and China one, and also South America one. And these 3 warming holes and occurring all in the middle of the continent. In addition, they are in eastern slope of major mountain areas. In U.S., it's east of Rockies. In China, it's east of Himalayas, and in South America, it's in east of Andes. And they are in intensive agriculture areas where it's plenty of soil moisture and also deep crop roots. It's bringing water through evaporation, which is suppressing warming that has cooling effect. And lastly, they are all at the terminal of low-level jet, where it's MCS and also moisture convergence are prominent. So these are common features of the warming holes. And in terms of U.S. warming holes here, and I plotted the second half of 20th century. And here, and top is third quarter of the century, 51 to 75. And the bottom panels are 76 to 2000. And you can see here it's warm cooling. The blue color is cooling. Actually, it's more severe or more advanced and in third quarter, and both in southeast and also central. And in the last quarter of the century, like summer and winter is very different. And winter actually warming a lot, and summer is cooling. Actually, originally I gave the name warming hole. It's this area in summer and within the central U.S. So from now on, when I say warming hole regions, pretty much in this region. These all are trends. It's not temperature itself, it's trend. And keep in mind, trend is difficult to capture than mean temperature itself. Here are the models I used. All in all, it's 25 models. And these blue ones also I used for attribution studies. That means including historical HGH, greenhouse gas simulations, and natural forcing simulations. Here is an array of 25 models and showing summer temperature, maximum temperature. As I showed, it's the warming hole phenomena is in summer, and more important, it's in daytime. They use maximum temperatures. And you can see the models, it's everywhere. And maybe one model which is access and got this warming hole very well. And some other models maybe get some a flavor of it's warming hole, which means cooling. And those areas, some got areas, but it's shifted in locations. And also a couple of models is totally out of lunch. It's somewhere here. It's warming. But this just gives the flavor of what model is doing. And if you summarize simply just the arithmetic average of all models and over 3 time periods, and this top is 100 years, the whole period of 20th century, and second is second half of 20th century, and this is last quarter. Actually, if global warming actually in the last century pretty much is contributed by this period. And you can see it's for longer periods, model average can get some and less warming, not cooling, but less warming. It has a tendency to capture the warming hole here and also a little bit in central U.S. But when period getting shorter and shorter, it's difficult for models. On 25-year scale, it's difficult to capture the cooling regions here. And overall, here it's a warming during summer. Maybe you can see a little bit less warming, but still overall it's a warming. Again, this trend. So the shorter period is harder for model to capture. And this is a trend. Again, all I'm talking about trend. Again, trend is difficult to simulate. Temperature itself is easier, but trend is harder. It's secondary derived variables. It's noisy. And here, and I just see the temperature trend over the warming hole regions. And top is 100 years, and bottom is 50 years, and left is summer. I think it's right is winter, and red is maximum temperature. Blue is minimum temperature. All are in trends. And just for example, seeing here, and this one and is the observed. As we see, it's actually cooling during a 50 period, cooling more than half a degree, and maximum cooling more than minimum. And these guys are model ensemble average, and the all remaining bars are each models, maximum and minimum. And you can see from here, active models almost did not get this cooling event at all. And again, we are very picky in asking model to pick up the anomalous cooling and the global warming environment. And here it's top, it's 100 years. And over 100 year scales, and some models get a flavor of cooling and compared with observations. But still, it's difficult to get the cooling trend. And now I shift gear a little bit for diagnosing what causing this anomalous cooling. And one of the debating question about this warming hole, whether it's the internal variability of climate system or externally forcing phenomena. And here I show, and left is the natural forcing, and right is greenhouse gas forcing. And natural forcing includes its aerosols from volcanoes and others. And so you can see it has a cooling effect over central U.S. And greenhouse effect has a warming effect. And both are summer. All of these ones are summer, but just a different period. Therefore, and one answer is here, and is greenhouse warming is not causing the cooling. And on the contrary, it's causing warming in the middle of the continent, which is, I think, it's inconsistent with general beliefs, because warming more at interior and compared to coastal areas. Next slide here showing the difference between historical and historical nature. Historical is including all forcing, including HGH, and including natural forcing, and more important, land use changes. So the difference reflects effect of greenhouse gas and land use forcing. And previous slides showed greenhouse gas and causing warming effect. Now these two together causing a cooling effect. This is negative cooling effect. Therefore, implies and land surface changes has a strong cooling effect over central U.S., even stronger than greenhouse gas. And here it's a different period. It's 50 years, and later 50 years, and it's less. It seems reasonable because land use changes it started in earlier, and later will change less during the century. And this bar plot just summarize and the temperature change and the different experiments. And this is greenhouse gas forcing only, this is natural forcing only, and this is all forcing. And apparently this and it's the more or less it's a sum of these two. And if you may recall, these patterns are similar to global and attribution experiments done by other studies. Therefore, model seems difficult to catch the regional and abnormal cooling, but these still follow general trend of global situation. Again, we are picky to ask the model to pick up regional and short period and abnormal events. Lastly, I will talk a little bit about record-breaking statistics. And this summer, and there was drought here in the U.S. And July, there are 4,420 station time break or tide high maximum temperature, and only 300 and broke low minimum temperature. And on the other hand, for relatively cold July 2008, and 500 stations and broke their maximum records, and 600 and broke their minimum record. Therefore, and how many numbers low breaking and high breaking is a good measure of climatic change. Therefore, I study the climate change, study the record-breaking temperature statistics to see how model capture those things. And here, just a little background. And suppose you have a stationary and random number time series, and your chances to break a record is decreasing as your record getting longer and longer. And for example, your July 1st temperature, you have 50 years of July 1st temperature. And if it's the first year, you are a record. It's high record, lower record. The second year, you have only half a chance to break record because it compares previous one and this year also, and so on. So as time increases and your chances breaking records getting high, more difficult and more difficult. The pattern is 1/n, like this. Of course, in the climate or temperature is not stationary. If you have a trend, so you have a one correction term, which V here is the trend. So you have a effect of second term, trend effect. And here, as example, here this is the over US. This is work done by Jerry Mears and Anchor. And here the curve, this black curve, is 1/n. So, and these red ones are the maximum record, and blue one is lower record, minimum record. Therefore, so your maximum is higher, is more frequent, and then stationary. And it's blue, which is the minimum record. It's quite lower than and statistics or theoretical value. And this value, for example, after 50 years, so your record per year breaking about 3.7. So on average, statistically, you have 50 numbers, and the 50s to break record chance is 7.3 per year. Of course, each year you have 365 days. And here it's in China, and this is all US. It's in China, it's very clear. You will see it's high, it's more, much more than and statistical value. And the blue one is much, much lower than and the expected values. That means you get fewer and minimum record and more maximum record. And if you
I'm breaking in just to let you know that we've surpassed 15 minutes.
Sure. Okay. And here you see, if you put the curve here, and you will see, and after the trend, your curve, your observation for fit curve is quite good. That means your trend explain quite a bit more how extreme weather recently is happening. And here is the ratio. Okay, it's the high to minimum record ratio, and this is the observed. This is the model. Actually, CSM4 pretty much good, and earlier it's less than 1, and now it's 3 or 4, 2 or 3 around this area. And here it's the monthly. Before I talk about daily and monthly, here the observed, if you can see, the low minimum is going down and maximum going up. And these models, some models producing it's the opposite, like a maximum is going down, and blue it's on the track. And this summary, I think I just stop here because time is up. Okay, I think.
Okay, thanks a lot, Zaitao. And thanks to all the speakers for excellent presentations today. What I'm going to do is unmute the phone lines and see if we have any questions. Okay, so are there any questions on the phone line for any of our speakers or all of them?
Hey, Dan, this is Jim.
Hi, Jim.
Hi. I have a quick question for Andy, if he's still on the line.
Yeah, sure.
When you showed the time series of minimum sea ice extent, so the September values, and you focused on where the models were underestimating the downward trend towards the latter part of the record in the post-2000 time period, there's also some times earlier in the record, like in the early 1960s and early 1990s, when the models are overestimating the downward trend. There's actually upward tick in the sea ice extent. And I was wondering if you had any thoughts about those. I mean, are those just like random things, or are they associated with volcanoes, or what do you think's going on?
I think I know exactly the slide you're or the uptick you're talking about. You know, I don't know if that is associated with any particular climatic event at all. I think we're seeing just random variability in the sea ice extent record that, and there's absolutely no reason. I think that if you look at individual ensembles, you see those same kind of patterns, but they're not occurring at the same time as, and you have no reason to expect them occurring at the same time as observations. So I think that some of it might be to do with volcanic eruptions, some might just be to do with particularly either cold conditions or wind has a great impact on sea ice extent as well. We're using satellites to measure this, and if wind pushes the sea ice out, then we observe greater extent. So it's difficult to tie down exactly what is causing those upticks.
Great, thanks.
Hi, this is Anarita. I have a question for Zaitao.
Yes.
I seem to understand your results point to a role for land use change you know, in forming these swarming holes, and I was wondering if you knew what kind of land use changes were prescribed in the models, and if you had an idea of what could be, you know, playing a role there.
Okay, thank you. Yeah, the question I think I discussed with other people also. I think agriculturally, it's from years to years, and the crop yield increased more at about 0.5% each year for last decades. So when yield increases, the biomass increases, and also evapotranspiration increases. And that's my guess. Or if their ET increase, they are suppressing warming, and that's what hardly explain why they are in the agricultural regions. Does that make sense?
Okay, thank you.
Are there any other questions on the phone line? Okay, well, if not, I'd like to thank Justin, Jinan, Andrew, and Zaitao for the excellent presentations today. Our next webinar is November 13th, Tuesday, starting at 1 o'clock. It's going to be continuing this topic, but discussing 21st century projections in the CMIP5 data set. And we are going to have 4 speakers, Eric Maloney, who, like Justin, has led the authorship of a multi-collaborator paper under the auspices of the CMIP5 Task Force that MAPP has organized. So he'll be talking about results from that paper. We're going to have Rim Sadek, Paul Diermeyer, and Chris Karnauskas also speaking during that webinar. So I hope everyone's able to come back and join us next month on November 13th. Thanks a lot for joining today.